Hey, hello there. Today's Leetcoding challenge question is unique binary search trees. So we have a positive integer number n. That stands for the number from 1 to n, integer number sequence 1 to n that we want to store using a binary search tree. And the question is basically asking us to count the number of structurally unique binary search trees that can do this job, store the number from 1 to n. The example, we have a number equal to 3, so we are looking at a binary search tree to hold the value 1, 2, and 3. And here in the example part, it shows you the 5 total distinct structurally distinct binary search tree that can hold value 1, 2, and 3. Since there are 5 in total, we return 5. So that's the question. How are we going to solve this? Notice that basically depends on the choice of the root node. The question can be broken into 3 different smaller problems, right? So if we choose one, we're going to count the number of structurally unique binary search tree when 1 is picked up as a root. And it's going to be the similar question for if we pick 3 to be the root node. What are the number of structurally distinct binary search trees that can do the job? And 2, so on and so forth. Basically, we're just going to divide the question into 3 different smaller problems and add those numbers together. So let's think about one particular example. If we pick, let's be a little bit large than 3 here. 1, 2, 3, 4, 5. If we pick some middle numbers, 3 as a root node for this problem, how many structurally distinct binary search tree are there if 3 is picked as the root node? We start to think about, we need to think about the property of a binary search tree. The definition for a binary search tree is actually kind of recursive. If we pick a node, randomly pick a node inside the binary search tree, of course the root node included, the left subtree has to be another smaller binary search tree with values no larger than the parent node. The right subtree has to be a smaller binary search tree with the largest value no smaller than the parent node. So if we pick 3 as the root node, the left subtree has to be a binary search tree with 2 values. And the right subtree has to be a binary search tree with another 2 values. So we can get the number of trees from both sides by just calling this function with a smaller n. And then basically just going to return those 2 multiplied by together, because you have 2 choices on the left hand side, you have 2 choices on the right hand side. Then the total variations you can have is 2 multiplied by 2, that is 4. So just going to put it down here. So we're just going to add total to be left multiplied by right. And we're basically just going to do for root in range 1 to 5. Right hand side is exclusive, so 1 to 5. We're going to do this. So that's basically we divide the problem into n different smaller problems, and each problem it's going to be 2 recursive call, because once we pick the root, we break this number line into 2 sections, and for each of the section, we have to build a binary search tree to hold that many different number of nodes, and we basically can use the function recursively to get the number of ways and solve the bigger problem. Before we're actually going to go about and code this, just going to think about the base case a little bit. The base case is basically if we have the root to be the very first node, that means the left hand side, the left subtree is totally empty. That's just one choice, one variation, one null pointer. So number of trees, 0 is going to be 1. And also, it's very easy to reason that if I just have one node to form a binary search tree, there's just one variation. So these 2 are the base case. Yeah. So with this, I think I'm good to go to code this thing up. So here, the first line we handle the base case. Then we initialize a variable to accumulate this total. and then we're just gonna pretty much just gonna copy the pseudocode here. We need to figure out the number of nodes on the left hand side, which is gonna be so the 2, basically, if you look at that's the root subtracted by 1. So that's root subtracted by 1. Right is going to be, we have another 2 in this particular example, which is equivalent to n phi subtract the choice of the root. Phi subtract 3 is equal to the number of nodes on the we have to form the right subtree, which is also a binary search tree. So it's n minus root. And then our total is incremented by those 2 multiplied together. In the end, we're just going to return this total. It should be a solution. But notice that we're going to have a lot of duplicated calculations inside this recursive function calls. So to improve the runtime, we can do a memorization. So with that, it should be a memorization version top-down solution. Let's see if it works. Okay. I have to add this here. So that's the top-down solution. Let's look at how we're going to solve this from bottom up. So basically, we can see what we are doing here using a loop is to break this calculation. Let's make a separating line here. N, that's equal to sum of some helper function over a choice of root and the total number for root in range 1 to n plus 1. And we can see that the helper function is basically this 3 line here. So we translate the helper function definition here, which is going to be calling this, but with a smaller input, smaller number. So root subtracted by 1 and multiply that by m subtracted root. So if we substitute this helper function definition back into this formulation, what we get is, just directly copy this and replace that. We get a double loop here. Sum, which is sorry, it's just single loop. We sum up over the for loop over the root choice, which is from 1 to n minus 1. To solve this, we basically see that to get the number for a larger input, we have to first calculating this number, smaller number of trees. So we can solve this by populating this 2 first, and just using this formula to gradually populating the number inside this 1D array here. So that would be the bottom-up approach. So that's going to be a for loop from 0 to n to gradually populating this 1D array, and every iteration in every iteration of that loop, it will be a nested for loop to go from the choice of the root and looking up at the prior calculated number and populating this new number. So that's going to be the bottom-up approach. So yeah, just gonna code it up really quickly. I'm sort of like in a rush now because I have clothes in the yard and it's started raining. So, really terrible. Yeah, so just gonna call this number of trees, and it's gonna be 0, and we pre-allocate n plus 1 location because we have to deal with a number of trees from 0 to n, and the base case are the 2 case here. So the loop is gonna populating the n from, because we already populated 0 and 1, we just go from 2 to n. And inside each iteration here, we're gonna enumerate over all the possible choice for the root. So that's gonna be I, and we're basically just gonna have this I to increment this by the two branches. So that's going to be I subtract the root subtract the 1, right? The reason being that sorry, this is the number of nodes we're looking at, and this should be left, and so we're iterating over this one less than that. Then here is the left. The right hand side is basically I subtract the left subtract the 1. So yeah, that should be the relationship, and we're just going to return the very last one. Does it work? Nope. Jeez, I have to hurry. Yeah, so this is the bottom up. I have to go.